Okay, so now our last type of chi-square test procedure for this course is a chi-square test for the independence of variables. And now this is indicated when two categorical variables are measured within a single population. One variable will be labeled horizontally and the other will be labeled vertically, which will produce our table of values or our two-way table. Now, the major difference between independence and homogeneity is subtle. So for homogeneity, I ask one question in two groups, such as the color preference of shirts between different genders or the opinions on a political issue between different political groups. Now, for independence, I ask two questions in one group. For example, I'll ask my AP Stats kids who is right-handed and who can wiggle their toes or who can wiggle their eyebrows or etc. But essentially, it's a 2 for 1. So in homogeneity, I ask one question in two groups, whereas in independence, I ask two questions for one group. And then don't forget our goodness of fit, I only look at one categorical variable in one population. So each of these combinations determines which of the three chi-square procedures we'll use. So same thing in our state part, we will say that there is no association, or we claim that these two categorical variables are independent of one another. However, I'm trying to prove that there actually is some association or dependence between these two categorical variables. Again, alpha will be 0.05 unless otherwise stated. Our conditions have not changed. We need random samples, independent samples, and our large counts condition, which means that each of our expected counts is at least 5 so that we can conduct a valid chi-square procedure here. And if these conditions are met, we'll use a chi-square test for independence. And notice the mechanics are identical to that of homogeneity. And they relatively say the same thing, but again, just that technical two populations versus one population versus one variable versus two variables. So again, the expectation we can find using this handy-dandy formula. We'll find the test statistic by adding up all of the contributions, the degrees of freedom by multiplying the row and the column totals minus 1, and then finding our p-value by using the degrees of freedom to determine which chi-square curve we will be using. Now, if we can reject the null hypothesis, it's because we have enough evidence to suggest that the two variables are dependent, or here, if we fail to reject the null hypothesis, we do not have enough evidence to suggest they're dependent. Let's take a look at an example here. Students at a large suburban high school take an annual survey to determine problems among students at the school. Each student in a simple random sample was asked to name one problem at the school, and the following results were obtained. So here I'm looking at my juniors and seniors. 24 juniors felt that there was academic pressure, 27 seniors felt that there was academic pressure, giving me a total of 51 students who thought there was academic pressure. And same thing, each of these rows gives me a new total. And then it appears that I have 129 juniors in my sample and 134 seniors in my sample to give me a total of 263 students who were interviewed in this sample. Now, based on our expectation formulas, I'll take 129 times 51, divide that by 263, and get about 25.02. I'll take 129 times 90, divide that by 263, get about 44.14, etc. So essentially, I'm just multiplying the row and the column total and then dividing by the total amount to find what the expected count is in the long run. Of course, I can't have 0.14 of a person, 0.75 of a person, but again, this is the long run average of how many students would say that this is an issue. Now, we can see that each of our expectations is greater than or equal to 5, and these are cut off here, but it should say 26.98, 45.86, 40.25, and 21.91. Now notice too that if I were to add all of these up, I would get 129 for the juniors. Or if I were to add horizontally, I would get 51, 90, 79, 43, etc. So in this long run average, we can see that it still comes out to the total that were included in our sample. So this just means that in long run sampling, I would obtain these results. So, is there a relationship between the classification of the respondent and the type of problem identified? Basically saying, do seniors struggle with one issue more than juniors, etc. Now, classification of respondent and type of problem are independent. I believe, no, doesn't matter whether you're a junior or a senior, the pressures are the same. However, we have evidence to suggest otherwise, that perhaps classification is dependent on what type of issue they might suffer with. Now, we can also make a graphical display here, such as side-by-side bar charts, or a segmented bar chart, or even a mosaic plot. But for now, we're just going to run the chi-square procedure to see if we have evidence to suggest that our observed and our expected difference is significant. So we've stated our hypotheses. Now we're going to move to the assumptions. Here I can assume that I had a random sample of 263 students. I'm going to assume that since this is a very large high school, that 263 is less than or equal to 10% of all students at this high school. A bit of a stretch to say 2,630 students at a high school, but totally possible in some very large urban areas. Now, as we saw from our expected counts matrix, all of our expected counts are at least 5, so we're good to go. And since our conditions are met, we are going to use a chi-square test for independence. Same thing, I'm going to calculate my chi-square test by taking the difference between observed and expected and squaring it. So I do so as follows for each of my 8 categories here, and I obtain a test statistic of 15.83. Now to find the degrees of freedom, I take my 4 pressures minus 1, which will give me 3, and I take my 2 classifications minus 1, which gives me 1, and 3 times 1 will give me 3 degrees of freedom. So the probability of obtaining a chi-square test statistic as large, if not larger, than the one we found, assuming 3 degrees of freedom, is 0.0012. And again, this comes to us from our CDF function in the calculator. And since our p-value is less than our significance level at alpha, we are going to reject the null hypothesis, which means there's sufficient evidence to claim respondent classification and type of problem are dependent. And now to figure out where that association exists, I could graph these with the segmented bar chart and see which social issues tend to be highest, and also what the difference is per social issue between the juniors and the seniors. But currently, since I rejected the null, that's going to show me that each of these pressures has a different weigh-in in terms of problems addressed by our students here. So it's not that each of these problems is faced equally, but some problems might have more pressure on students than others. Alrighty. So that's just an example of our chi-square test. And here are a few multiple choice questions. So go ahead and pause the video, attempt these out, and then we'll come back and review them together. And if you just stumbled upon this online, this is awkward, but we'll come back and review the answers here shortly. Now, a survey of 75 people with jobs at a mall was conducted to determine whether they worked in retail, and the two-way table shows the responses by gender, male and female, retail or non-retail. Which of the following best describes the association? And you might be thinking, Mr. Pinto, isn't this a chi-square test of homogeneity? Well, we didn't take 2 independent samples from between 2 different populations. We took 1 sample here of 75 people, and then within those 75 people, we broke it down into their type of job as well as their gender identity. So we can see again 1 population, so our 1 sample, and 2 categorical variables here, gender identity and job type. Well, if I go ahead here, there appears to be an association since the proportion of women that have retail jobs, here the 26 out of 52, is much larger than the proportion of men who have retail jobs. And sorry, I looked at it in terms of retail, but I need to look at it horizontally. So that's 26 out of 31 versus 26 out of 44. And so you can solve this problem either using a chi-square test statistic, making a segmented bar chart, or even just calculating the proportions or probabilities to best determine that association. And then the last one here, again, the following is from a random sample of employees at a large company. Again, they're classified as managers and non-managers, and satisfied and non-satisfied. If the null hypothesis is that there is no association, and between these, it says it's true, what is the chi-square test statistic for the sample? This means that here, it's saying the null is true. And if the null is true, we should fail to reject the null hypotheses. This is a correct decision, thinking back to our types of errors in power. So to find the chi-square test statistic, I would do 60 times 115. I mean, we're here, right? Might as well do it. 60 times 115 divided by 155. that here is going to give me 44.5. And you know what? I'm already tired of doing this. But basically, if I did 60 times 40 divided by 155, 95 times 40, blah, 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 you get the picture. And then I were to sum up the differences between the observed and the expected, square that, divide by the expected. If I were to add up these four contributions, I'd get a chi-square statistic of 0.0335. My degrees of freedom here, 2 columns, so 2 minus 1, times 2 rows minus 1, only 1 degree of freedom. So this p-value comes to us from the probability of getting a test statistic as large, if not larger, than 0.0335. And that gives us this p-value here. Now, notice this p-value is larger than any reasonable significance level. So here we fail to reject the null hypothesis. If we fail to reject the null hypothesis and the null hypothesis is true, we've made a correct decision. So here, our results of our calculations do verify that we would fail to reject the null hypothesis. Thus, since the null is true, we don't want to accept it, but we want to fail to reject it. As of now, this stands as our best decision. So that's just some insight on the 3 different types of chi-square procedures that you'll see on the AP exam. It makes up a very small proportion of the AP exam and usually on the form of only a few multiple choice questions and then the occasional FRQ for any one of these 3. So just as a recap, the goodness of fit is used when you're looking at one single categorical variable in one population. Now, if we look at 2 categorical variables within one population still, that's a chi-square test of independence. Whereas if I look at one categorical variable in 2 separate populations, that becomes a chi-square test of homogeneity. So there's like a flow chart you can follow here, but basically ask yourself, are you looking at one population or 2 populations? And are you looking at one categorical variable or 2 categorical variables? Homogeneity and independence follow a very similar structure, but goodness of fit has its own few mechanics that you have to take into account. So if you're still confused, go ahead and rewatch any of the last 3 videos. But if not, I will see you all in class so we can do some activities with the chi-square distribution.